think what we're going to cover this week is something a little bit different. So we're going to be looking at using the SolidCAM plugin for SolidWorks. So just like we've been doing with the simulation tutorials, I think it's probably best if we use the remote desktop version of SolidWorks so that we're all using identical copies of SolidCAM, and it avoids people having to ensure that their local copy has got SolidCAM installed as well. So for this particular session, I'm going to use the remote desktop as well. So one thing that I have found when I've been using this is occasionally I get a little bit of corruption on my screen, but if that happens, just resizing the screen slightly like this seems to cure it. It seems to redraw and then everything is fine. So if you notice me doing that as we're going through, that's why I'm doing that. It's not corruption at your end, it's at my end, but I can get it to refresh and to correct that just by resizing the window slightly. So before we begin, I'll just draw your attention to that link at the top of the learning materials that's been there all the time. Link to general SolidWorks tutorial videos and everything that we're going to cover in the next two sessions, which is going to be SolidCAM based primarily, is available there in sort of 5 easy parts. So if you need to refer back to this at any point in the future, you can look at this recording of this particular session, or probably it's more useful to come in here and just browse to the section that you need. So yeah, all of the same content is there. The wording might be slightly different, but we achieve the same kind of outcome at the end, which is that we create a little SolidCAM program to machine a box that we're going to have a look at in a minute. So all of that being said, the 2 files that you're going to need to download are a little bit further down the page. So if we scroll down a little bit, in the SolidCAM section there's a testcam solid part file. So you're going to need to download that. And there's a matching file which has got the file extension PRZ. So that is a SolidCAM file, but you need the 2 files together. So you need to download them into the same folder as each other. And we'll talk a little bit about the SolidCAM files and their relationship to the SolidWorks file that we use to create them. But if you want to get those 2 things downloaded, drop them into a folder where you know where they are, obviously. And then when you boot into SolidWorks, so I've already got SolidWorks running in the background here. Initially, we're not going to touch SolidCAM. We're just going to have a look at the SolidWorks part that we're intending to create a CAM program to hopefully machine. So this is just opening a normal SolidWorks part. So we go to the open file icon. You can already see a little bit of that corruption coming on my screen. So I'll probably just do a quick resize. So where are we? I think I dropped them into my documents on this machine. And if I browse in there, yeah, I think that's the correct part. I'll just double check. Testcam solid part is what we're looking for. Yeah, that's the wrong version, but I think we'll load that one in. So basically this is it's a part that I've specifically modeled up to allow us to experiment with different types of machining operations within SolidCAM. So it's not of any particular use. It's got elements of other parts that I've designed in the past that were parts for manufacture. But all the features on here are just to give us something to practice our SolidCAM machining operations, or the setup of our SolidCAM machining operations. So if we have a quick look at this, if we go to the feature manager, we can see the features that build this box up. It's a simple kind of rectangular box. It has a few features on the other side that we weren't looking at there. So if I rotate that round, you can see it's got some through holes on this side with counterboard heads on them. It's got a little piece of lettering on the other side, just an X, which has been kind of engraved on this side of the box. It has various features down in the sort of indented portion on the other side of the box. Whoa, this remote desktop's not the quickest on my machine, so I'll have to go careful when I'm rotating models around. So it's got various features on this side, and as I say, what we're intending to do is we're intending to set up a SolidCAM part to allow us to create machining operations that will machine away portions of a solid block in order to arrive at this box shape once we've done all our machining. So we're just having a quick look at it first before we actually go ahead and do that. So now that we've had a look at it, what I'm going to do is I'm going to shut that down, and I'm going to load in the ready-made SolidCAM file that you also downloaded. So this is the SolidWorks file that we downloaded. In order to shut that down, we don't have the X on this version, so I'll probably go to the File menu, click on Close. That file will shut itself down. So the first thing, to open a already existing SolidCAM part, it's not as easy as just going into the File menu, clicking on Open. We've got to actually go into the Tools menu. And one of the first things that you notice there is there are two menu options that sound very similar. There's SolidWorks CAM, which is not what we're going to use, and then there's SolidCAM. So just as a little aside, various versions of SolidWorks, so whether you have the student version or the student engineering kit or the full professional version or the premium version, there's lots of different versions of SolidWorks in terms of how much it costs to actually purchase in the first place. And some of those versions come with a built-in add-in called SolidWorks CAM. So the version that the university's paid for comes with that built-in add-in. But that is not the program that we're going to use to do our CAM machining in. We're going to use the third-party software called SolidCAM. So don't make that mistake. As I say, SolidWorks CAM and SolidCAM are not the same thing. So we'll be using SolidCAM. So that's what you're always looking for. And what we're going to do is go to Open, because we want to open an existing SolidCAM part file. So we'll click on Open, and then we'll have to browse to wherever we saved that file. I've already been playing around a little bit before we began this session, so I've got 2 copies of this file already. But it's this one that I'm going to open. So it's the one that you downloaded, essentially. And it's got a PRZ extension on the end of the file, or it should have. So yeah, if we click on that and click on Open, and the system should load that in, you may get some pop-ups saying this is created in a previous version, and the next time that you save this, it will be updated into the more recent version. You can essentially click on OK on all those pop-ups that you're going to get. Someone's just asking, is there a way of gaining more storage on the university computers? Yes, because it is a little bit stingy. 100 meg, it runs out fairly quickly. So if you send a nice email off to IT help and just tell them what course you're on, tell them you're on an engineering course and you're generating quite large files, and they do have a policy of just upping your limit. But you have to actually request it. They don't give it as a sort of pre-made higher limit. But I've never known them refuse up to this point in the years that I've been teaching this. So yeah, just send them an email. Just outline what course you're on, the fact that you're doing CAD sort of work, some analysis work as well. and they should be happy just upping your limit. I'm not entirely sure what they up it to, but it's a lot more generous than the default amount. So yeah, that'd be my advice for that. So when we've loaded this part in, the reason that I've provided this is for us to kind of have a guide on what we're aiming to create. So this is the part that you downloaded, but it has all of the machining operations already created in here. And what we're going to have a look at before we start to create these machining operations ourselves is what these operations look like when we simulate them within SolidCAM. So in order to do that, there's a few things that you'll have to do first. As I say, I've already been in here before this session, so probably what you're looking at has little sort of asterisks, little black asterisks to the left of all these operations here. And that means that they're all out of date. It means that the file that got loaded in, something's just occurred to me. As it brings that file in, it will probably say something to the effect of, the part file that this model refers to cannot be found. Do you want to find that model yourself? To which you want to click yes, and then you want to point the system at the SolidWorks file that you downloaded. So you downloaded two files. One was a PRZ, which was your SolidCAM file, and one was an SLD PRT, which was your SolidWorks file. And when you initially load this in, it has a problem, and it's basically saying to you, we have the SolidCAM file, but we can't find the corresponding SolidWorks file. Would you be kind enough to point me in the right direction? So you have to browse into the folder where you downloaded the SolidWorks file as well, double click on the SolidWorks file, and then it will say something to the effect of, that's fine, do you want to update the link to this new name? And you click on yes. So I've already done that, which is why I'm not getting that as a pop-up at this point, because I've already done that and saved a copy out. So when you drop into this interface, when you've done all that, all of these machining operations will be what's known as out of date. That is that since you updated the SolidWorks file, they haven't been recalculated. So in order to do that, you right click at the top level here where it says operations, and you click on calculate all, and it will run through them all and recalculate them. And then probably what you'll get is you'll get the path that the various tools will take around your part and across your part to remove those pieces of material. So you can see those being created on my screen. These lines represent the center axis of the cutting tool as it passes backwards and forwards across my part. So when we get to that point, what we can then do is right click again where it says operations and click on simulate. This is where we simulate the actual block of material being cut into our final form, into our box shape. So I think what we'll do a quick run through at high speed first, and then we'll come back in here and we'll play with some of the options. So you want the options selected that I've got here. So you want this first one clicked, which is show toolpath. You want this second one on, show hidden lines. You want this one, which is show the actual tool that's doing the cutting in 3D. We may as well have the tool holder switched on, although I don't think I've spec'd any tool holders in here. You want show data switched on. So this will show us things like how fast the tools are spinning and how fast the milling machine is pushing them through the material. It will give us a running total in terms of time taken as well, which is quite significant later on. We want solid verification switched on, and I think, yeah, we'll have show stock switched on. So you want it selected as I've got it on my screen there. And then we're going to push the speed up to its maximum. So you can see I'm clicking and dragging on this simulation speed. because initially we just want to do a first pass. We want to see what these cutting operations are actually going to achieve. And when we've got all that set, I'm going to click on the play button underneath, and we will see tools zipping around over our block of material, gradually removing that material and revealing the shape of our finished part. So that's essentially what we end up with. So that's a little bit busy at the moment. There's quite a lot of things on the screen. So I think what I'll do is I'll turn off the path of the tools. So you can see, as I was saying earlier, that is the center line of each tool as it passes backwards and forwards across my part. So let's turn that off, which is that first icon there, show tool path. So I'm going to click on that and then run through again. So hopefully what you can see, various sizes of tool get called up. So we're using, I think this is a 6mm diameter tool, and then we'll probably change to a slightly smaller diameter tool. There, that one was slightly smaller. Now we've gone back to the 6 again. We'll probably get a drill to put the holes in here in a second, although it'll be really quick. And then a much bigger diameter tool to do the outside, and a really small one, if you caught it there, to machine this O-ring groove for the top of the box, which if I zoom in a little bit, you'll get an appreciation of what that is. It's a little kind of trough that runs around the top of the box. And the intention there is that this box could potentially be made watertight by picking a off-the-shelf O-ring size and sizing the perimeter of this groove to the appropriate length for that O-ring, so that you could drop the O-ring into this groove and actually put a lid on this box. And when you crank that lid down with the bolts, it will actually make sure that the box is reasonably watertight. So that, in sort of a nutshell, is what we're looking to achieve. But we were running that at very, very, very high speed. The actual time to complete all those operations is almost an hour at the moment. So you can see 55 minutes is what we're reading for the overall time of that simulation. So what I'm going to do is I'm going to leave this copy open on my machine so that I can refer back to it and talk about how these various operations have been set up. So you can see the first one that occurs here is one that removes the stock material off the top of our block of material. And then we move on and we kind of dig out some of the material in this internal pocket that's kind of accounts for the majority of the internal shape of the box. And then we've got other things such as we've got drilling operations and tapping operations and various other operations. So I'm going to leave this open, but in order to have two SolidCAM parts open at the same time, I'm having to run 2 copies of SolidWorks on this remote desktop. So you don't have to do that. So what you should do at this point is close this part down like this. So File, Close. And it will disappear, because I'm going to guide you through the steps to actually create a new SolidCAM part. So just for my purposes, I'm going to bring that part back, because as I've already said, I'm going to refer back to that as we go through. That's sort of our guide, our recipe, if you like, to actually set up our new SolidCAM program. So you don't have to load it back up. I'm going to talk you through creating a brand new one, but I'm going to leave that in the background. So I'm going to flick to my new copy of SolidWorks. So this is a second copy of SolidWorks running on remote desktop. And in order to create a new SolidCAM file, you first have to have loaded up the SolidWorks part that you're intending to machine. So that's what you've got to do first. So we know how to load up a SolidWorks part. We just go to File, Open. It should navigate back into the same directory. Yeah, there's my SolidWorks part. I think mine's named slightly differently to yours, but it will be the name of the downloaded part. It will bring the SolidWorks part in not in SolidCAM at this point. So we can just look at that. We can look at the features, just as we were when we kind of started this session. And then from there, now I can create a new SolidCAM part. And SolidCAM assumes that I want to create it using the thing that I have on the screen currently. So you load the SolidWorks up first, and then go to the SolidCAM part tab, or you can get to the same point by going Tools, SolidCAM, New. So you can see there's two options in terms of how to launch a new part. Probably the easiest way on these particular remote desktop installations is going through the SolidCAM part tab. So SolidCAM part, New. It then basically asks you what sort of CNC machine are you going to use to machine this part. We're just going to use a simple mill. So I click on mill. Then there's a little bit of setup and options that I can change if I want to before I actually get into setting up my SolidCAM part. The first option here is whether I want SolidCAM to generate its own SolidCAM files, or whether I want it to hide them inside the original SolidWorks file. So these are the two options here. My personal preference is to create a discrete separate file. It kind of makes file management a little bit more logical in my head, at least. So that's the default on these systems, so that's good. So when we save our SolidCAM setup, it will save out a file with the file extension PRZ. So it will save out a file that will look a little bit like the one that we were just poking around in. So we'll leave that set as it is. We'll probably give it a new name. So given that we've already got one of these SolidCAM setups already saved on our disk, it'd be nice to be able to differentiate this one from that one. So maybe I'd add new to the end of the name of this one. That seems reasonably sensible. And then this next option, which I have ticked, which I think the default is to not tick it. It's renamed it now back to, will it let me rename that? Nah, I shouldn't have pressed enter there. Yes, I have to press enter to get it to accept that name, new. What I was talking about there before I mistakenly pressed the enter key was that last option that I had ticked was asking me, do you want to store your new SolidCAM part file in the folder where the SolidWorks file came from, or in a separate folder? And my preference is to always store it in the same folder as its SolidWorks part file parent, if you like. And again, it just makes file management a lot easier. If you keep your SolidCAM files in exactly the same folder as your SolidWorks files, the chances of you doing what is known as orphaning the SolidCAM file is far less likely. And when I say orphaning it, I mean passing it maybe to a colleague or taking it to a different machine and forgetting that you also have to take the SolidWorks file as well. Because that's how SolidCAM kind of is set up. It needs a reference back to the SolidWorks file that created it. It kind of doesn't function at all in isolation on its own. So if you ever pass a SolidCAM file to somebody else, you're going to want to pass them the SolidWorks file that was used to create it as well. So yeah, that's a little bit about file management. But we accepted all that, so I pressed enter to accept that new name. And I drop into the initial setup of my SolidCAM file. So there's kind of three broad areas in here. Well, four, I suppose, if we talk about selecting the type of milling machine. So the drop-down list here has got various CNC milling machines, and I think there's some mill turns in here as well. So there's various CNC machines, many of which reside in the basement in the sheath building. So at some point, if you get back in there, you can go and actually have a look at these in person. So these set up how we'd like the G code that we're going to generate formatted. So depending on what manufacturer your machine is made by, so we have various manufacturers in here. There's Mazak. We've got some Haas machines. I thought we did have. No, we haven't. But yeah, we've got machines from various manufacturers. And if you want to think about it like this, they all speak slightly different languages. The language overall is NC code, and it obeys certain rules, but every manufacturer sort of puts their own little twist on it, so that you need what's known as a post processor in order to make your CAM program compatible with whatever CNC machine you're going to run that program on. So in our case, we're not going to get into that level of tailoring our CNC code to a particular machine. So we're going to pick what I consider kind of the most sort of plain default machine that comes with all copies of SolidCAM. So this isn't a specific one that's been supplied to the university. It's common across all installations of SolidCAM, and it's this one, G-Milling 3-axis. So that one there, G-Milling 3X. That's the one that if you install a student version of SolidCAM, that you should have that particular post processor. I thought mine had quit out there. It's just very, very slow, this remote desktop on my machine. So I've set the CNC machine that I'm intending to use to actually cut this material when I've generated my CAM program. The next thing I'm going to do is I'm going to work through these options lower down, but rather than setting up my coordinate system, which is what this first button does, I'm going to go and set up the size of my block of material that I'm going to begin with. So this is referred to as the stock. So the piece of, let's say, aluminium that I'm going to insert into the CNC mill before I begin any machining operations. So this is what I'm defining now. So I click on stock there, takes me through to another interface, very, very slowly in my case, but it'll get there in a second. And essentially what we're going to do is we're going to use the inbuilt SolidCAM tools to create a kind of cuboid of material that encloses our box that we're hoping to machine. Wow, this is running slow now. Oh, it's still thinking about it. I'll just keep checking on it and just check that it hasn't completely gone to sleep. So yeah, we're going to create a block of material which is going to be slightly bigger in our case than our finished box size. And that will allow us to machine a certain proportion of that material away and arrive at our finished box size and shape, having machined the faces of the box, rather than the alternative, which would be ordering up a block of material that was touching the outermost faces of our box, in which case we couldn't run a cutter along those faces because they would already be on size. So we create a box of material that's slightly bigger than our part to enable us to then trim back using our cutting tools, so that we know the surfaces and the faces of our finished part have been accurately machined. We haven't relied on a aluminium supplier to accurately cut their stock material perfectly. So what are we going to do? I think what we'll do is, I'm trying to set all the settings here as they were set on the version that we were browsing through. I'm going to add 5 mil of material on every face of my box, except for the underside of the box, which I'm going to add a little bit more material on. I'm going to add 20 mil of material. So what we're going to do is we're going to start typing 5s into all these initially. So 5, 5, 5, 5 and 5. And then the step that I've just skipped over there, because I was talking and not thinking, was we have to point the system at a particular piece of solid geometry in order for it to know what size and shape it is adding these 5s onto. So currently it has nothing selected in here. So we have to point at our part that we've brought in. Because in some cases you can bring multiple parts in, so you will point at one of them in particular. So the way that we do that is we click on the button underneath where it says selection, CAD selection, and then we can just click on any face of our box. And then click resume, and it should collect our box as a solid piece of material there. It's collected the box shape as its reference size and shape of thing that we're hoping to machine once we've completed all our SolidCAM operations. And then when it's analysed that, it's looked at the extents of that shape in X and Y and Z directions, and then it's just added 5 mil of extra material beyond it in all directions. So you can see that if I look at it broadly from sort of the front, there's 5 mil of material above, there's 5 mil of material to the right, to the left, on the bottom, and the same on all directions. So that's what we've set up currently. But I said before we came in, I wanted extra material on what I'm considering the underside of the box. So that would be down here. So we have to tell the system that, and that is in the -y direction as we're looking at it now. So you can see my direction arrow icon at the bottom left there. The Y direction is pointing up, so that is positive Y. So I want to add extra material in negative Y. So if I go to negative Y, put 15 in there, and then press enter. Or rather, it didn't update when I pressed enter, but when I clicked into one of the other entry boxes, it does update the graphic. And the reason I'm adding some extra material on there is I already have in mind a method that I'm going to machine this box. So I've kind of thought ahead, and I've thought that I'm probably going to clamp this box down in my milling machine so that the milling head approaches the box from this direction. So we're looking down onto the internal of the box. So the milling head is coming from this direction, and it's going to be spinning round, taking material out. But in order to do that, I have to come up with some method of clamping my stock block of material to the table of the milling machine. And the way that I've decided to do that is to just use a vise that is itself bolted to the table. So I'm giving the vise a little bit of extra material here so I can get some square vise jaws sitting on these side faces or these front and back faces without interfering with my ability to machine some of this geometry up here. So I need that extra piece of material in order to clamp the vise jaws onto. And then when we get a little bit later on in this exercise, probably next week, and we've created all this geometry on this side of the box, we then create a second setup where the CNC machine operator would unclamp the box, flip the box over so that the machine is now approaching it from this side, and then we could address these through holes and these counter bores and the engraved X, which is on this side as well. And again, we'd have to come up with some method of clamping it. I think it's when I discussed this with the CNC operators in chief, they had a few suggestions. One was you could use a vise again. You could just put soft jaws on the vise so it didn't damage the machine faces that you created on the box. Or you could create a plate which is bolted into the CNC machine, which is essentially a jig. And then you could locate on the jig using some of the bolt holes. The problem is with that, in order to create the counterboard side of each hole, you would have to stop the program every so often and remove one of the bolts. So maybe you could bolt it here and here initially and tackle these two counterbores, and then you would have to stop, swap the bolts over, and tackle these two. So yeah, there are various ways, but initially, certainly, we're creating a bit of extra material on the bottom section here in order to give us something to clamp onto with our vise. Now, as I've been clicking here, I've inadvertently got rid of my selection. So I'll just click back on the box there just to reselect my box shape. So when you're looking at that, you can click on OK. I missed another step there. I'm good at missing these steps. So what I'm going to do, I'm just going to drop back into that stock menu again. So I didn't mean to exit it there. And I want to click an option, which is this option here, which is going to add a representation of the size and shape of my stock to my actual model itself. And that's quite useful because otherwise, if I don't select that, I'll do it as a little experiment now. So I'm just going to exit without clicking on it. That cage that represented the stock size disappears. It doesn't get created. It's been stored by the system. The system has a record of it for its own purposes, but I, as the user, cannot click on that box anymore. So that's not as useful as when you exit that stock menu, clicking on Create or Add Box to CAD Model. So when I click on that, initially nothing seems to happen, but now when I exit this menu, I get a version of what I was just looking at retained. And the reason I've done that is the next step that we're going to do is we're going to drop a X, Y, and Z coordinate system into our machining setup. And this would be referred to as, there's many names. There's the part coordinate system or the part 0 point. But this is essentially where all of the commands to move the CNC machine in X, Y, and Z all end up at 0 wherever we put the coordinate system. So just in the same way, when we're creating parts in SolidWorks, we have an origin. We call it the origin, but I think we talked about that is just the point where the x-axis ends at 0. It doesn't actually end, it transitions from positive numbers to negative numbers. But the x-axis is at 0 at that point, the y-axis is at 0 at the origin point, and so is the z. So it gives the system a reference as to where things are placed within 3D space. And the CNC machines work exactly the same. So we have to decide now, where are we going to put that 0 point? Where are we going to put the part coordinate system? And I like to put it on these sort of one-off jobs. I like to place it on a corner of the stock material because that's quite easy when you're running the CNC machine to put the stock material in, clamp it down, and then you can use the CNC head itself to actually clock or measure where each face of that stock material is. So you can tell the CNC machine, our coordinate system, for example, is sat at this back left corner of our stock block. So yeah, that's what we're going to do next. So click on coordinate system. When we eventually get into this menu, there are various ways of creating these coordinate systems. One way of doing this, and I think I've covered this in the videos that I was pointing at the kind of outset of this session, is that you can create the coordinate system in SolidWorks before you get to this point. So you can insert coordinate systems into parts while you're modeling the part. But this one in particular, I didn't do that because I wanted to look at how do you create a coordinate system on the fly as you're setting up a SolidCAM part. And there are tools in here to do that. There are various ways of doing it. The one that we're going to use is just the define option here. You can see if I'd brought a coordinate system in, I could select the select coordinate system, and it would give me a list of the coordinate systems in this SolidWorks part. But yeah, we're going to define a new one. And there's three things that the system needs. It needs the point in space where we want this coordinate system to be. So I'm going to click one of these points on the edges of my stock cage or my stock wireframe. So that point there, when I select the point, it then moves down to the next piece of input that it requires. So it wants the X direction. And generally, in most CNC machines, the X direction would be considered the longest amount of travel that the machine table can do. So often on CNC machines, the horizontal movement has a longer axis and a shorter axis. And generally, when we talk about x-axes, we talk about whichever one of them is longer. And again, very generally, the access doors that you would open to put stock into a machine or remove stock from a machine, the x-axis tends to run parallel to the access doors. That's not always true, but generally. So X direction, I'm going to use that back edge there as my reference to tell the system what direction I want to call X. So click on there. It then moves down to the next piece of input, which it's asking for, what do you want to consider the Y direction? And again, convention is that the X and Y axes in normal mills are the horizontal movement axes within the mill. The Z tends to be considered the axis that the spinning spindle can move up and down. So Y direction, I'm going to tell it, is that leg of my stop box there. And then it infers the direction of Z. So you can see it's given me a little graphic showing me the orientation and the position of that coordinate system that I'm about to create. Now, Z in this case is pointing down into the part. There are various schools of thought as to whether Z should be positive down into the actual stock block itself as we're looking at it. I think of the people that I've spoken to, various CNC machinists and CAM operators, the general consensus is Z should be pointing away from the material which is to be cut. So what I'm going to do in order to achieve that is I'm going to use some of these options down at the bottom, which flip my coordinate system around one of the axes. So if I click on flip around X and then click on it again, that is more acceptable in terms of what we want. So Z is now pointing upwards. So I'm going to click on OK there. Then I think I get taken into the menu. Yeah. So I don't think we're going to touch anything in here, but it's worth knowing that this menu exists because we can get back into it at a later point. So there's things in here to do with where our tools start in terms of Z. So this is 70 millimeters higher than what we are calling 0 point on our Z axis. So that would be the top of the stock here. So the tools start 70 millimeters above there. They can then travel at an incredibly fast speed down to 50 millimeters above 0 point. But then they transition to moving in a much slower, much more conservative speed range. So this clearance level and the tool start level to a lesser degree is concerned with trying to avoid hitting things at an incredible speed. So above the clearance level, the tools will zip around in X and Y and Z very quickly in order to minimize the time needed to actually move them into position. But below the clearance level, they will move at a much more reasonable, much slower speed. So if you're looking to get time gains out of your CAM program, you could reduce this down, but you're always running the risk that you will then maybe impact a clamp that you hadn't accounted for, or some piece of geometry on your part that you hadn't accounted for. So this is a safety sort of clearance. There's other things in here that it's the system has inferred from the SolidCAM part that we've brought in. So it's analysed it and it's seen that it's 100 mil deep. Yeah, but generally we kind of don't play around with that, certainly at this point. As I say, we may double back and at a later point try and get some speed efficiencies into our program, and we may come back into this menu. But at this point, we'll click on the green tick to OK that one, and we should drop into our SolidCAM main environment. Aha, no, one more menu first. So what this menu is telling us, and again, we're going to click through this at this point, but it's worth remembering that it's here because we're going to need access to this later on in this process. So what this menu is showing us is currently we have a single coordinate system within our SolidCAM program. And this coordinate system is the coordinate system that we're going to use to conduct all our machining operations on this side of the box. So as the machining head approaches this side of the box, it's using this coordinate system as its 0 point for all 3 axes. But then when we come to address some of the features that are on the other side of the box, they can't be reached or can't easily be reached without some very, very strange machining practices by approaching the box from that direction. So the initial direction. So what we're eventually going to do is we're going to create a second coordinate system that is related to some of the features that are on this side of the box. So this is what we would see if we'd set that coordinate system up at this point. We'd see that we had our initial coordinate system here, and then we could add a second one in. We could reference some geometry on this side of the box for this coordinate system, and it would say position 2, or it would say Mach 2 position 1 actually. So yeah, we're going to come back in here and add a second coordinate system, but we're not going to do that just yet. So in terms of the coordinate systems manager, we can just click on the green tick. And then at this point, do we drop into the final menu? No, we just got to do one last check. All of the rest of the settings here, we're not going to touch because they're governing things that we kind of don't need to use in this very simple SolidCAM setup that we're about to create. So all of this iMachining data, we're kind of not going to use any of that. We don't need to go in and change any part settings. We're going to leave program number settings as they are and everything else. So the broad outline of that is pick your milling machine, create a stock box, add a coordinate system. The system then automatically populates this target window by analyzing the SolidWorks part that you've imported. So it looks at the SolidWorks part that you've imported, and it says that is obviously the target that you're aiming for after all your machining operations have been complete. So the stock is the beginning point, target is the end point. So we'll click on the green tick because we don't want to change anything else. And at this point, we drop into the SolidWorks interface, SolidCAM interface proper. So here we are. So we're essentially in a new tab that sits alongside the feature manager tab there, and some of the other tabs that we've kind of seen are available when we're running just SolidWorks on its own. This new one's been added to the end now, and this is the SolidCAM manager. So it's similar to the interface that SolidWorks uses. The people who program SolidCAM have tried to adopt some of the appearance and the methodology of how SolidWorks, the interface works, but it's not identical. It has its own kind of quirks and things that we have to learn how to deal with. So at that point, what I'm going to do is I'm going to just zip back to my other copy of this that I have open in the background so that we can have a look. What is the first thing that we want to create? The first operation that we want to create. So it's this operation here, which brings a rather sort of large diameter tool into our SolidCAM setup, and it sends that tool in what's known as a hatching pattern across the top of our stock box. So you can see there, the tool begins there, so that is 70 mil above the top of our part. It then comes down to this level here. It does a pass across the top of our part, removing material as it travels along here. Then it moves over a set amount, and then it returns again at the same level. And it does this several times until it gets to the end of a pass, and then it rises up above our part and then goes back to its starting point before dropping down to a slightly lower level and then taking another slice off the top of the part. And if we want to see what that actually looks like, it looks something like this. If I just slow it down. So there's the tool, backwards and forwards, dropping down each time, taking slices off until it reaches the surface, which is the top of our box there. And you can see the preview of the actual machined stock material here, which is in this sort of grey colour, is kind of fighting for supremacy with the kind of bluey grey of our SolidWorks model underneath. You can see if I move my viewpoint, the two surfaces are sort of fighting each other to be visible. And that essentially means that the machining operation that I've just done has machined down so that it's reached the level of that surface in my SolidWorks part. So it's done its job. It's removed the top stock, which is why I gave it that name, remove top stock, which we'll come on to in a minute. Once we've set this thing up, it's good to name your operations, give them specific names that you can interpret, because that makes it easier if you have to come back in and modify them at any point. Just leaving them all with their default names makes your life, or possibly somebody else's life, much more difficult than it need be. So let's create that operation to actually remove that stock material. So the way that we create a new operation to remove some material is right click on operations, go down to add milling operation, and then pick the type of operation that you want to create. And you can see there's various, or there's quite a lot of different ones in here. The one that we're going to use is known as a face mill. Because we use a tool known as a face milling tool, and we kind of address a whole face of our stock material. So face mill is what we want to create. And broadly, we work down these menu options from the top to the bottom. We often don't have to get all the way to the bottom option before we can get the system to calculate the path of the tool. So generally, if we address the geometry option here, we give the system a tool, give it a level that we want to machine to. At that point, we can normally do what's known as a save and calculate for this particular operation, and the system will show us a preview in the graphics window here of what the path of that tool will look like. So this is kind of when you're setting these operations up, it can be quite hard to visualize purely from these numerical entry boxes what this cutting operation is actually going to do. So as soon as possible, my advice is, when you've given it enough input that you can press save and calculate and see the actual tool path that you're going to generate, do that, because that may give you extra information that you'll then think, oh, hang on a minute, I missed something there. I actually wanted to click equal step down, or I actually wanted to set my delta distance to something different. So yeah, it's very much sort of an iterative process where you do a little preview of the tool path, you make a tweak, you press recalculate, you see how it's affected the tool path, and backwards and forwards and so on and so forth, until you've kind of optimized each operation. But let's go back to the top. So geometry is broadly, what piece of geometry do I want this machining pass, this face mill, to address? So this is what we're going to tell the system at this point. And the way that we do that is click on the little pencil there, the new sheet of paper, because we don't currently have any geometry selected. So new, it's the same icon as new part file icon. And there are various ways of selecting geometry in here. The one that we're going to use, because we want to target this tool to address the entirety of the top of our stock material. So I'm pointing at the outside edges of the stock material there. So we want to bring a large spinning face mill down, and we want it to take the entire surface of our stock material away, down to a certain level that we're going to specify later. So in order to do that, I'm going to not click on my finished SolidWorks part shape, because that is smaller than my stock block. So I'm not going to click on the model. I don't really have any faces because of the way that the stock representation has been created. It's what I'd term a wireframe. It's actually a collection of 3D sketches, but it behaves just like a wireframe. There's no face there that I can click on. There are only edges and points to describe its size. So I can't really use the faces option either. So the only one that I'm left with is profile. So profile. When I click on profile, these menus lower down then sort of rejig themselves. And basically what this allows me to do is it allows me to select lines, if you want to call it that. The system refers to it as profile, but it allows me to select lines of one type or another. So that's perfect for my purposes, because what I have is a collection of lines that I want to be able to click on to define the external size of my stock. So I click on the define button and then wait, because we're using the remote desktop. And then all I'm going to do is I'm going to click on one of these edges that encompass the top of my stock piece of material. It doesn't matter which edge I click on. So I'm going to select this one here. And the system, because it has some smart selection tools built into SolidCAM, it sort of makes an assumption. And it makes the assumption that I'm going to want to select a closed boundary of edges that are all connected to each other and that are all on a common Z level. So it then highlights what it thinks I want to select and then asks me this question: is this all right? Is this what you want? If I didn't, I could click no and start clicking on other edges. But in this instance, that's perfectly fine. So click yes, and it selects them all. And as I say, the reason it's selected them all is that that option has been ticked by default, constant Z. So that does what I just said. It looks at the Z level of the thing that I just clicked on, and it looks at anything else which is at that Z level. So that edge is at the same Z level, so Z being vertical here, and that edge is, and that edge is. And then it realizes it's got back to the original point, so it stops looking, and it offers me those as an option. And you can see them there. Chain 1 is a chain or a series of connected edges. So that's what it's going to address with the cutting tool. So when the cutting tool, we're going to do this a lot, looking from the perspective of the actual cutting tool itself, looking down onto our part like that. That is the perimeter shape that it's going to address. So that's kind of half of the specification of what we want it to cut. The second half is how deep do we want it to cut into the part. But that's the geometry portion. The one last thing that we're going to do, well, we're going to click on tick here to accept that geometry. It will then back out into the previous menu, having collected that geometry. So you can see chain 1 is now in that chain list there. The one thing that we are going to do is we're going to add an offset of 2 millimeters and then click apply and watch what happens to the geometry that's now highlighted in this window in pink and in yellow. So enter 2 and then click on apply to all, and then it jumps outwards by 2 mil in all directions. And the reason I've done that is to account for inconsistencies in our stock material. So inevitably, when you get these blocks of material, they've been kind of not very accurately machined away from a larger piece of material. If this was aluminium, it's often cut with a huge saw, which will sort of not very accurately sort of hack its way through the larger block of aluminium. So you can't rely on these side faces being square or even being flat. So it's always best to put a little bit of allowance so that the tool that you're about to call up to make some passes across here assumes that the stock material is slightly bigger than it should be. So that's why I've put that 2mm offset on there. And at that point, we can click on OK because we've defined that geometry shape. So we've addressed that first option there, that first icon. And it's been entered. And if we want to check out what that shape is at any point, if we come back in, we can click on Show, and it gets represented in the window there. And then we can go back in and edit it by clicking on that Edit icon. But we're happy for the time being. So we've done that. Next thing that we're going to do is we're going to tell the system what sort of tool we want to use for this operation. So currently, we haven't spec'd any tools at all in this SolidCAM setup. And one of the ways that you might work if you were running SolidCAM in a large organization is you would keep certain lists of tools in a library, and you could call them up at this point. You could say, I'm going to use machine whatever. I'm going to use this CNC machine. Do we have a set of standard tools that we tend to run that machine with? Yes, we do. Right. Can I have a list of them? And then there would be a corresponding list already set up inside SolidCAM, and you can just bring that list in. But we don't have any of that. We're doing everything from sort of first principles, if you like. So what I'm going to do, I'm going to click the only option that I've got available to me here, which is Select. That drops me into the tool manager, which is empty at the moment. So I want to add my first tool into this tool manager. So I click on that icon, which is a big plus sign in green. And then you may not be able to recognize that, but it's a tool being held in a tapered tool holder that you would use when you were using a CNC mill such as this. So click on that to add a new tool. You get given some options. What sort of tool do you want to create? I think we'll create a face mill, given that we're doing a face milling operation. So face mill. We get a little preview, which at first might not appear as if it's a 3D representation of the tool, but if you middle click on it and drag, you can see that that is a 3D version of the tool shape that we're kind of setting up here. So you can see it has a certain diameter to it. The yellow portion of that 3D preview represents the teeth of the tool itself. So you can see currently this tool is able to cut to a depth of 20. So that the height of that yellow there, which represents the teeth, is 20 millimeters from the end here. So we're going to modify this slightly. So we're going to use a tool which is 80 millimeters diameter. The intention here is that this tool will be of a type that uses small inserts to do the actual cutting. So you can see the graphic down here, which is kind of a generic face mill in graphical form, has these little diamond-shaped inserts that are held within a body. And as the tool spins, it's the inserts themselves that actually cut the material away, which is in contrast to a more traditional sort of slot drill or end mill, where the tool itself is made out of some sort of hard material and it has teeth actually machined onto its surface. So yeah, the point I'm making here is this cutting height or cutting length here on these sorts of tools tends to be very, very small. They're not very good at cutting a lot of depth, but they are very good at removing a lot of material. They come in quite large diameters. So let's put something realistic on here. Let's say 5mm only, like that. And you can see the 3D preview update in there. So that's going to tell us if we try and cut 6mm and bring this tool into a block of material and it's 6mm deep, the system should flag that and say, whoa, 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 you've just hit the material with the tool where there's no cutting face, and you've arguably broken the tool or damaged your stock material or damaged the CNC machine. So this is one of the things that we're trying to catch when we're creating CAM programs in software like SolidCAM. We're trying to do all these little errors and get to the bottom of them and erase them from the program without having to actually endanger the real CNC machine or waste time coming across all these little errors. So at that point, shall we leave that tool? No, we'll address the speeds and feeds sides of tool setup. So if you were setting a real tool up to do this job for real, what I would do is I would get on to a typical tool manufacturer's website and I would spec a tool that actually exists. So one such website is Sandvik Coromant, who have got a pretty nice tool selection and tool information online sort of interactive tool, if you like. Find a tool or find cutting data. I can never navigate to the location that I want. I believe it's find a tool. Or maybe I'd be better off going to Google and typing Sandvik Coromant tool selector. My point is, manufacturers such as this give you a really good sort of wealth of information that you can enter into your SolidCAM programs. It's gone to sleep again now. We'll come back to that. But yeah, I would recommend them particularly because they have some really nice online tools for selecting the correct cutting tool, and then they can supply you with all the data that you're going to need to enter into this tool data tab, which is how quick should the CNC mill be moving this tool around in X and Y when it's cutting the material, how quickly should the tool be spinning, so how many RPM should the tool be spinning at, and other things such as how much material should it be cutting on each pass that it passes over the material or passes through the material. So how deep should it be cutting, and how much of its diameter should be engaged in that cutting action? Should it be half of the diameter, or should it just be the edge portion, maybe 20% of the diameter? So all of that data you can get by actually going to manufacturer websites. Here we go, we've come back again. So tool selector, there we go. Sandvik Coromant tool selector. Find the right tool. That option there. So if I've come to the right place on their website, I have. Brilliant. So this is a really useful sort of tool to allow you to select your cutting tools. So what are we trying to cut? We're not creating anything on a sort of lathe setup, so it's not rotating, so it's non-rotating. What is it that we're trying to cut? We're trying to cut a plane surface or shoulder, I think is probably the nearest to what we are trying to achieve, just a plane surface cut. Plane surface with interrupted cut, no, it's not a shoulder, so it's just a plane surface. Then there's other options here. So my intention with this one would be that it's made out of aluminium. So I would go in here and say, do we have various types of aluminium? Yes, we have an aluminium which is broadly 90 on the Brunel hardness scale. So I would maybe select that one. What sort of CNC mill am I using? How many kilowatts of power does it can it supply? What is its maximum rotational speed? So I could select whichever sort of mill I wanted here. And then what sort of operation type is this? It's not particularly a finishing operation, so let's call it pre-machining. Depth of machining feature. So I think we're taking 5 mil in total. You get the idea. You can go through here and spec what you're trying to achieve. And then when you've done, you click on Get Results and it offers you up some different tools to do the job with. So we've got one here which is very similar to the one that I was describing, that has these gold coloured tips held in the tool. And if that is the one that we want, then we can go and get some cutting data. So we've got an overall diameter. We've got a maximum depth of cut of 6 millimeters. So I set mine at 5, but we could tweak that. And then if we click on here, I think we get some of the cutting data. Where are we? Da, 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 da. My screen's corrupting slightly now. So maybe it's one of the other options. I think if you have a play around in there, you should be able to find it. Oh, here it is. So cutting speed. So this is giving us data that we can then feed in terms of setting our rotational speeds and how quickly we push the tool through the material and how deep we should be taking for each cut that we or each pass that we do on the material. Working engagement is what I was talking about before. How much of the tool should actually be doing cutting work? Should it be 50%, which I think was the recommendation there? So that's, 50 millimeters. So 50 millimeters from, I think it's around a 80 millimeter diameter tool. So that is quite large engagement. There's not much of the tool that's not engaged in actually cutting slices. But anyway, that's a good reference to populate some of that cutting data. I'm trying to get back. Here we go. Some of the tool data in there. But let's say that we've entered all the relevant data. So we're happy with that tool. We click on the green tick. That tool then gets selected as the tool for this particular operation that we're creating. So we'll move down to specifying the levels of this cut, or how deep do we actually want to cut into our stock material. So the way that we spec this is by selecting actual geometry from either our part or our stock box as we are representing it. So the upper level, if I click on upper level, I can select some piece of geometry that represents the top surface of my stock material. So I could select one of these edges. It's not letting me select the point. So I'll probably pick that edge there because that is at the top of my stock material. And then I click on the green tick to OK that. That is unsurprisingly referred to as 0 because that's where my coordinate system is sat. So I said the coordinate system sits at the point where all the axes tend towards 0. So that's why that's been entered as 0. Face depth, so this is the depth that I want to arrive at after I've created this face mill. So click on face depth, and it's the top face of my finished design. So in this case, the top face of the box there. So I can click on there. It will put a little red point on there and it will highlight it and it will tell me what level below the coordinate system that is. So it's in the minus, so -5. Click on OK. Then I get to specify what sort of step down depth I want to use for this. And I think for this setup, let's have 2. So I'm just going to put 2. So I'm imagining a tool that's only able to cut 2mm depth slices off in each pass. And that's just to make our machining passes a little bit more interesting for this tutorial. So at that point, I've entered enough information that if I want to, I can calculate what these cutting paths are going to look like. And the way that you do that is that icon there. So the second icon in, which if you hover over it, is save and calculate. So if we click on that, the machining passes should appear in the window and I can sort of inspect them and see if I can appreciate what's going on. So there's that's interesting. So it's doing a step down initially of 2mm, or it should be. And then it's doing another step down. The reason I'm sounding confused there is, given that we're cutting 5mm of material away, and I've allowed this tool to cut a maximum of 2mm, I would have expected it to drop to 2, do a cut. It is doing. So yeah, this is the first cut here. This is the first cut level, and this is 2mm below the top of the stock material and below the coordinate system. So that takes a slice off the top, and it hatches backwards and forwards across the part like we saw before. And then it gets back to its starting location, and then it drops down to 4mm. So at this point, it's at 4mm underneath the coordinate system. And it does the same hatching pattern backwards and forwards. And then it returns to the starting point a third time. And then it drops down to 5. So you can see the gap there is only 1mm. So if I wanted to affect that, I could say, well, the tool's only capable of cutting a maximum of 2mm at any one time. So I can't increase that. I don't want to decrease it, but I could share out the cuts equally. So if you click on that option, equal step down, it will take 2 as the max that it can do, but it will divide the total down into as few steps as possible, whilst respecting the fact that 2 is the maximum that it's allowed. So if I click on save and calculate, it respaces the passes again to equal out the actual amount that's cut away on each one. So I think, unless I've forgotten anything there, I think we'll okay that operation. We're broadly happy with that. Let's do a quick simulation just to check that it is doing what we think it is. So from within the actual operation window itself, we can run a simulation as well. And it's that icon there. So click on simulate and probably then zoom out a bit so I can see the part a little bit better. And then click on play. And the big face mill comes in and kind of hatches backwards and forwards across the part. It gives me a running total in terms of the time. If I zoom in a little bit, I'm getting that slight sort of battling for supremacy between the two surfaces there, which I'm going to take as my indication that we have actually reached the correct level. So yeah, I'm broadly happy with that. So let's move on to the next operation. So I'm going to quit out of the simulation. I'm then going to do one last thing in here, which is to rename this operation. As I said back at the start, it's useful to rename them, give them specific names so that you know what they're doing. So I think I did top stock remove for this one. And then I'll just do a final save and calculate. And then I'm going to exit. So that's that icon at the bottom right there to exit. And what you might have noticed, every time we create a new operation here, we're going to do that save and calculate option. So the manufacturers of SolidCAM have integrated you regularly saving your part with all the times that you need to calculate what an operation would look like. So the reason I'm mentioning this is often people are very confused when they come to shutting a SolidCAM part down. They can't figure out how to save it. So when we are working on a SolidWorks part, we just go to the File menu, click on Save, click on that Save icon possibly. SolidCAM, every time you do a recalculate, it takes a save of the part. So it's doing exactly what it's saying it's doing. It's saving the part onto the hard disk. So in that respect, it seems almost wrong to do, but as long as you've just done a save and calculate on a preceding operation, then you should be safe to just exit SolidCAM or exit SolidWorks in its entirety, knowing that that has now been saved. It's been updated in the window, it's been calculated, but it's also been saved onto the hard disk as well. So we'll get to that right at the end of the session, and we'll kind of prove that it has actually been saving in the background. So let's create a new operation. So I don't want to view the toolpath of that one anymore. So I'm going to deselect it. So I want that little box at the side of it to be unticked. And the next operation that we're going to do is to kind of dig out or remove some of the material down inside this kind of cavity that is the inside of the box. So SolidCAM refers to these sorts of operations as pocketing operations. And the general term for this sort of indented area where all the material's been taken away is a pocket. So we're going to use a pocketing operation to kind of remove a certain quantity of this material, but we're only going to allow the pocketing operation to go down to that level there. Because what we're going to have to do, we're going to have to create an initial pocketing operation that comes down from this level on the top of the box where we have taken the stock material down to with that face mill, and it's going to dig away inside this pocket shape until it gets to that level there, and then that will be an operation in and of itself. And then we'll create a second pocketing operation that will take material away from this pocket shape, but it will start at this level and it will only go down to that level there. And then we'll do a third one, which will just address this little pocket inside there. So you can see that there's a sort of self-contained pocket shape. We'll address that one, but the tool that addresses that will begin at that level there, because these pocketing operations are gradually getting deeper and deeper and addressing the various features that occur further and further down on the Z level in this larger pocket. And then eventually we'll do a final pocketing op. So we'll do pocketing op number 4, and it will begin at that level there that I've got selected, and it will machine material away down to the floor of the main pocket there. And then what that one will do is all the subsequent pocketing operations, we'll have told them to leave a slight amount of material on all of these vertical walls. And the reason for that is, if we machined all the way up to these walls at each of these varying levels, so if we machined all the way out to that wall when we were doing the pocketing up at that level, and then we machined all the way out to those walls when we were doing the pocketing up at that level, you would get what's known as a slight witness line. You'd be able to see the different levels that we'd machined to. Whereas if we leave a little bit of an allowance, only around about 0.2 or 0.3 of a millimeter on all of these walls, so we don't quite finish them to the correct finished size, then when we come in and do the final pass on this lower pocket, we can run round the inside of those walls at what's known as full depth. So we'll pick a tool that has teeth which are as tall as the entire pocket, so that we finish it in one single pass that runs round the inside. And that way we'll get a nice, accurate, visually nice sort of finish on the internal face of the box there, rather than getting slight little discrepancies and witness lines between the various levels. So that's what we're going to do. We're going to do lots of pocketing operations. So let's get the first one kicked off. So right click on operations, add a milling operation. Pocket is what we're creating. And then it will drop us into the interface, which is quite similar to the face mill that we created before. Most of these different type of milling operations have this kind of common interface style and method of working. Some of them have some extra tabs, like I don't think we had the technology tab, or maybe we did in the facing operation. But they all tend to have some form of geometry definition at the top. In all of them, you've always got to tell the system what tool you're going to use. Some of them have levels. A lot of the ones that we're using have the levels option. So yeah, we'll kind of get used to this style of interface as we work through a lot more of these. So let's go back to the top, geometry. So just as before, this is kind of giving the system a perimeter shape that we're going to need it to address. And it always helps to kind of view your part from the perspective of the actual cutting tool. So that's why I've rotated my window, so I'm kind of looking down onto the part. My cutting tool's approaching the part from this direction. So I need to tell it what is the perimeter shape, or what is the pocket shape that I want it to address. So hopefully you should be able to tell that it's kind of this. If I can select it, it's kind of that shape there. So I've highlighted it in blue. Excuse me. Yeah, so that is the broad sort of shape when viewed from above that we want the system to address. And given that we've selected a pocketing operation, the system kind of understands that we don't want it to address the outside of that line. We want it to address everything that is contained within that line. So everything that is bounded by that chain of edges that I've selected, that's what we want it to address. So I'm going to try and create that now. So just so I've got nothing pre-selected, I'm going to click in some empty space there just to deselect that line. And I'm going to click on New Geometry, just like we did before. And very similar to the way that we did before, I should only have to click on a single edge. So I'm going to pick that one there. So if you zoom in a little bit here and just rotate around, you can see hopefully that there's kind of there's a flat section there before that O-ring groove begins, and then there's an inner sort of shape which is part of the pocket shape that I just selected before. And I'm just selecting that little rounded portion there. And then what the system does, well, it does two things. It uses that constant Z option to select all edges that are both attached to my beginning edge and on a constant Z level. And then it offers me them as a question saying, are these the edges that you want? Now I know, even though that the zoom level that I'm at the moment, I can't see around the box, I know that it's selected the ones that I want. So I'm going to click on OK. What it's also done is it's mapped them up to the level of the coordinate system. So it does that. It maps them up to the level that we're calling 0. So that's why I appear to have 2 copies. So I'm just going to click on OK to select that. Then I can zoom out and sort of fully appreciate what I've just selected a little bit more. And yeah, we're broadly happy with that. That kind of defines the perimeter shape of our pocket when viewed from the perspective of Z. So I'll click on the green tick. So we've addressed geometry. Now we need to supply a new tool. So obviously that face mill, you saw the relative size of that face mill, that 80mm diameter face mill. It's far too large to expect it to be able to drop into this pocket shape and be able to remove all the material within here. So we're going to have to create a new tool. So I'm going to click on select again. It then drops me into the only tool that I currently have, which is that face mill. So I'm going to want to create a new tool now. So click on the green plus icon at the bottom left. New tool. I think we'll just use a flat end mill. You can see the various different types of tool here. Yeah, it's the most suitable one for what we want to achieve. So end mill. We get our 3D preview of what this thing's going to look like. And let's do some setup of this. So what do we want to set it as? I think we'll leave it as 6mm. I might just play around a little bit with the overall length. So overall length of 100. Now we haven't addressed setting up any tool holders at this point. And to be fair, given that this is sort of a theoretical exercise, it's just a tutorial, we haven't really stated what sort of CNC machine we're going to intend this to be machined on, if we were actually going to machine this in reality. And the reason I'm stating that is if you were doing this in anger as such, you were doing it for real, you would have a CNC machine in mind. That CNC machine would then entail some form of tool holding device that would hold your machining tools in place. So you would then go into this submenu and you would, for example, pick an existing tool holder which is on the market, and that would be added to your 3D simulation of your tool. So you can see that that is an option. But I'm going to forgo that, or forgo the requirement to do that, because this is just a tutorial. It's good enough that we understand that that ability is built in SolidCAM if we need it. And as I say, if we were doing this for real, we would definitely model up the tool holders or select a relevant tool holder from the library that's available in there. And the reason that we would do that is that when we simulate things with tool holders enabled, we can see whether the particular tool holder that we're intending to use would actually interfere with the part itself. So in this case, if we made our end mill short enough, so let's do that now. So let's take it down to 65. Outside holder, I don't know, let's go down to 35 if we can, like that. So maybe something as stubby as that wouldn't be able to get down into our pocket, or if we told the machine to put that down so that it was at the lower level of our pocket, the tool holder itself would actually impact on our part. So that's why you would enable tool holders, to try and catch those sorts of critical errors. But we'll switch them off for this particular exercise. But the reason I sort of did a little aside there is this outside of holder length is related to, well, how much of the tool is sticking out of the holder. But in our particular setup here, because we've got holders switched off, it kind of doesn't do anything at all, because obviously the holder isn't previewed in this 3D tool preview here. So what did I mean to do in here? I think I was going to turn the cutting length up to the max that I can currently, so 30 mil. The reason I'm doing that is I want a tool that's long enough that when I come to do this lower pocket, it can address the entire depth of the overall pocket, which is probably a good point to just check on that. So what I'm going to do, I am going to go into the Evaluate tab in the standard SolidWorks tabs at the top here. So Evaluate, click on the measurement tool, so the little tape measure, and then I want to measure the length of one of these edges. So you can see there's a vertical edge highlighting there, and I want to know what depth that is. It's 27. So I can be reasonably confident if my cutting teeth extend up the length of my tool by 30, I'll be able to cut the entire depth of that in one depth of cut. So that's what I'm checking for. One other thing that is probably worth checking for is the my Windows corrupting again. Just let me make it update. There we go. Right. So here's my measurement window. It was hiding behind my tool preview there. It's trying to hide again. I'll just put it in some empty space up there. So I want to deselect the edge. So I'll right click and go delete the edge. And what I want to measure now is the radius of that internal curve there, or even that internal curve there. And the reason I'm doing this is I want to ensure the diameter of this tool that I'm creating will allow it to get all the way into that internal curve there. So you can see that that is a curve of radius 7 millimeters. So if I was to create a cutting tool that was, for sake of argument, 20 millimeters in diameter, it wouldn't be able to fit into there. So it wouldn't be able to cut all of the material away in there. So as you specify tools, it's intrinsically linked with what geometry you're looking to cut. And are you intending to do what's known as a finish pass, where you want to cut the stock material to its finished size? And in this case, we are going to use this tool for that purpose. Not on this operation, but we want to recycle this tool in later operations as well. So it's just worth checking. But 6 mil diameter is going to be fine. So I'm going to shut that measurement tool down. Click on the X there. Again, if we were doing this for real, we'd go in and we'd enter some real cutting data. We'd go away. We'd do our research. We'd get some genuine cutting data and enter it in. I'm going to leave all mine on the default. Click on the green tick. And we've spec'd the tool. So there's kind of one last thing to do before we can get a preview of what this tool pass is going to look like. And we need to tell the system what levels we're cutting from and to. So upper level is going to be the level that that previous face mill took us down to. So that was the top of the box. So we can be confident there's no material higher than that currently in our part, because that face mill removed it down to that level across the entire top surface of the part. So I'm going to click on that face. So that's where I'm beginning from. So that's my upper level. Pocket depth, I've already said, we're only going to go down till we meet this island, which is sat in the middle of the pocket. So I'm going to click on the top surface of that island, like that. And it will measure how deep that is relative to the coordinate system. Now, the nice thing here, because these are highlighted in red, if at some point in the future I change my design for the box in SolidWorks and then save it under the same name, the next time I load in my SolidCAM setup, SolidCAM will notice that I've made a change, and it will say, you've made a change, do you want me to update everything to reflect the new change? So let's say this island depth ended up slightly higher, then this operation is dynamically linked to the height of that island now. And that's what the system is telling me there by the fact that it's coloured this box in red. Whereas alternatively, if I was just to type a number in here, which is what I'm doing now, that is not linked. That is just a static number. So that is not dynamically linked to anything. So if I was to change the model with the intention of machining the new version, the Mark II model, on every production run, that wouldn't come to pass. I would still be machining the Mark I because I hadn't linked this depth value to the actual model itself. So it's far sort of wiser to click on the button there, link it to an actual piece of geometry in the model, and then you know it's going to auto update. So the last bit here, what sort of step down is reasonable for a tool such as this? Let's give it 3 mil. And I've set it to equal step downs there. Yeah, let's have it as equal. Now let's do a save and calculate and see what the tool passes look like. So it's a little bit harder to see this one because there's lots of movement in there. Because it's such a small diameter tool, it's having to whiz round inside that pocket quite a lot. So the tool paths themselves aren't as useful because they're so densely packed, it's difficult to tell them apart. So I think what I'll do is I'll run a simulation instead. So click on simulate. We'll run it through a reasonably kind of low speed to begin with. We may ramp the speed up as we run through. So the first thing, let me just pause. The first thing is, because we've already run a simulation of our first operation there, that's stock removal, the stock block here has been updated to reflect that. So that's not always the case, but because we ran it in this session, it's taken a save of what the stock material looked like at the end of that first operation, and it's allowed us to begin this next operation with that already removed. So we'll keep running. You can see kind of largely it kind of tunnels in the center of the pocket down to the depth that it's going to cut to, so 3 mil or something along those lines, and then it kind of spirals out. So it steps out a certain amount on each kind of rotational pass that it does around. And then it eventually ends up with a shape, which is the correct shape for the inside of the pocket there. So you can see it stepping down, and we can see the feed and the RPM that it's running at. We can see the time. We can see the Z level relative to the coordinate system there. And obviously the X and Y are changing massively all the time as it moves the tool around. Some things to note here. One thing is, if we look down from above, which is easier said than done, so down from there. So if we look at the tool, there's a certain percentage of the tool or the tool circumference that's actually doing the cutting here. You can see all of this side is not cutting anything. It's not engaged in the work. And we can affect that depending on the cutting data that we can get from the tool manufacturer. There will be recommendations over how much step over, as it's known, the tool has, or how much tool engagement the tool will withstand without bending or possibly snapping. So if we want to have a little play around with those options and see how they affect everything, we can do in technology. Here we go. Minimum overlap is 50% of the tool diameter at the moment. So let's say we want it to be much kinder to the tool at the expense of taking much longer to do this operation. We could drop that way down to say 20. And then when we do a save and calculate and do a simulate again, and then zoom out a little bit, is it reflecting that change? Not sure that it is. Curious. Seems to have gone in the opposite direction. It's got way more engagement this time. Maybe I've sent it in the opposite direction. But it has affected it. So yeah, I'm going to have to read the wording on that a little bit more, I think. It seems to have gone to the other extreme. There's only kind of 20% here that's not actually doing anything. So let's have a little poke around in there. Minimum tool overlap, 20% of the tool diameter. Well, that is odd. I'm going to have to look at that. But we're affecting it, is the bottom line. So let's get the tool paths on and play with this figure. So if I drop that back to 20 and do a save and calculate and see whether the paths get further apart or nearer together. So they got further apart. So it appears as if I'm reverse affecting this. Ooh, that one's interesting. And then if we go to the other extreme and go to 90, yes, they're incredibly small. That's strange. I would expect that to operate in the opposite direction. But you can see the effect that that is having. And you can appreciate how much longer that quantity of tool passes would take than where we began, which was at 50. So that's all related to, it's the strength of the tool itself. If you're really unlucky, you will push the tool so much that it will snap. But more than that, what will happen before is the tool itself will begin to bend under the force of the material being cut by the tool, and you will achieve inaccurate cuts. So when you think you're removing material and you believe the tool should be held vertical, the actual condition on the end of the tool is that it's not vertical. It's been deformed slightly, like a banana shape. So it's been pushed away from where your program thinks it should be. So you end up with walls that have got an angle on them that arguably kind of their surface finish isn't that acceptable either. So all of that sort of cutting data related to RPM that the tool is spinning at, the feed in X and Y, the speed that it's been moved in X and Y, the amount that it's overlapping with the material, and the depth that it's actually cutting down in Z into the material will all weigh in to whether you're going to get a satisfactory cut or whether your cuts are going to be inaccurate and finished poorly. But we know that we've got the ability to affect all those things now. We've got the overlap there. We can affect the step down level in here. We can go into the tool setup and affect the feed in X and Y in millimeters per minute, the feed in Z, the RPM of the tool, all of these options. We've got the tools to actually, or the knowledge to actually change them within our CAM program. It just takes a little bit of research to actually find the real figures that you would want to enter in here. So let's do a save of this after we've renamed it. I think this was top pocket or upper pocket. And then press enter, and then I'll just do a save and calculate. Before we exit this operation, I would just want to do one last thing on it, which is I said that we were going to leave a little bit of material on the walls of this pocket. So the outer walls that are running vertically, I want to leave what's known as a finishing allowance. So I want to leave probably 0.2 of a millimeter on all the walls, so that when I get to that lower pocket, I can finish the walls as a single pass and get a better kind of surface finish to them. So the way I'm going to do that is I'm going to go to technology and just say, I'd like a wall offset, please. So 0.2. And then if we just zoom in a bit to that outermost cutting line there, when we press save and calculate, we should be able to tell that it's moved slightly inwards. So yeah, it did. It moved slightly inwards there. So it's leaving 0.2 of a millimeter on the outside of the pocket, which is what I intend for this one. So I'm going to click save and calculate one last time, just because I'm paranoid that it's going to crash at some point, and then I'm going to exit that operation. So let's turn the toolpaths off for that. And then I think that's probably, well, let's do one more operation, I think. So let's duplicate everything that we've just done, but let's take the tool down till it reaches that level there. And there's an easy way to do that, given that a lot of the setup of this next pocketing operation is just duplicated, or a duplicate of the setup of the first operation. So let's list some of the things that are the same. The tool that we're intending to use isn't going to change. There's going to be a pocket, which is described by this sort of edge here. But then we're going to have to tell the system something else. We're going to have to say, there's an area in the center here that we'd like you to avoid machining. So this is why we're doing this step as a separate machining operation, because it's not identical to the first one, but it does have a lot of similarities. So given that, we're going to take a copy of the first one to use as a starting point for the second one. So I'm going to right click on it, and I'm going to go copy, and then I'm going to go right click on it again, and I'm going to go paste, and I'll get a copy of my initial operation. And then if I right click on the new one there, I can go to edit, and then it will drop me into the interface that we normally come into when we're creating these operations initially. So the geometry is the first thing that I want to address. So unfortunately, it won't allow me to recycle that first chain of edges. I'm going to have to create a new set that contains both that first chain. I'm going to have to replicate it, but then also contains an island in the center that I do not want machining. So I'm going to have to create new. So I click on the new icon again. And then drops me into the familiar interface. So I'm going to pick an edge which represents the internal, or one of the internal edges of my pocket. So that one there. It will then use its helpful tools to try and figure out what I mean by that. It's got it right in this case, so I'll click on OK. And then I'm going to select a second chain of edges that kind of denotes the bit that I don't want machined, or the island. So I'm going to click on that edge there. And then hopefully it will be able to figure that one out as well. So it looks as if it's got that one right. So again, it's used some smart tools here. It's used the constant Z, but it's arguably used this one as well, tangent propagation, which means if an edge is tangent to its previous neighbor, select it. So it's used both of those tools, and it's come to the right conclusion. Is this the chain of edges? Yes, it is. And if it isn't, I'll reselect it. So yeah, it has done. So that is the bit that I want to avoid. And you can see I've got two distinct chains of edges there. So I'll click on OK. The tool I don't have to address because I'm going to reuse the same tool. So levels are going to be slightly different. So the upper level now is going to be the lowest portion of the previous machining operation. So that will be on top of that island. So that's where I'm going to begin my machining. And then the pocket depth is going to be down onto that surface there. So, okay, that. And again, these are values that are linked to the actual model itself. So if the model was to update, these values would update as well. And then at that point, I should be able to do a calculate and see what that toolpath is going to look like. So save and calculate, and it appears reasonable. And this one will already have that wall offset set to 0.2 of a mil, because it was a copy of the original pocketing operation. But we'll just check that. We'll go into technology, wall offset, yes, 0.2 of a mil. So this isn't the upper pocket, it is the mid level pocket. So I'll probably just call it mid pocket. Do a save, and shall we take a copy of this to do the next one down? No, we'll not. So I'm going to exit that now. So at that point, I think we'll probably pause it. We're definitely going to continue this one next week, because inevitably the SolidCAM portion tends to take a couple of weeks to get to the end of the actual machining of the box. But we've done all the sort of initial, we kind of are a bit familiar with the interface now. So we should sort of accelerate slightly next week and be able to add some more operations quite quickly. But in terms of taking a save of that, you should at this point just be able to exit and everything will be saved. So it won't run over Easter, but I believe it's timetabled for after that as well. So yeah, it's Easter next week. Sorry, I meant the next session. So refer to the timetable. Yeah, sorry about that. So yeah, it'll be on your timetable. Just keep an eye on it as to which date it actually pops back up again. But I actually mean the next session, whenever that may be. So I'll consult my timetable as well. But yeah, we should just be able to, if we have just done a save and calculate, which I'll check that I have just done. So I'm editing that mid pocket now. I'm doing a save and calculate. And then I'm going to go File, Close. It's offering me to save it all anyway. I would probably click on Yes, Save All at that point, just to be on the safe side. So it shuts that down. Now I'm going to test that it has taken a save of it. So I'm going to go Tools, SolidCAM. And again, pay attention at this point that you don't go into SolidWorks CAM. They could have been a bit more generous with picking a different name for these two, or maybe switching the SolidWorks CAM add-in off on these systems, but it's SolidCAM that we need. So SolidCAM, recent CAM parts, or let's do an open. So double click on that top one. Give it a second. It looks as if it's fine. It's just thinking about things. There we go. So we're back in again. So yeah, that's how you load it back in. But we'll pick that up again on the next session, whenever the next session may be. But yeah, keep an eye on your timetables and we'll come back in and we'll continue that one. So yeah, I'll see you all next time.